Yeah, it's a great pleasure for me to be here, and thank you very much for the invitation. It's particularly a great pleasure for me that after so long time where we all had to stay at home, we finally are able to meet old friends here in Madrid again. And I hope that not in not too far future, we also have the opportunity to meet again at Cern in a more regular way. So I have the task to tell you a little bit about the future of particle physics from the Cern point of view. So I took the freedom to interpret future actually from today until maybe the end of this century, how it could be. Now, this is a bit the outline. I will use as the red line throughout the presentation the European Strategy for Particle Physics. I will, of course, talk about the LHC, the future program of the LHC, and then also the next project at Cern, which is being studied now, which is called FCC. And if there is some time left at the end, I will also leave the colliders, the big machines, and talk a bit about diversity program on other interesting experiments that we have in mind. So this is a reminder of the European Strategy for Particle Physics. You don't have to read and understand everything. I just want to point out that this gives the orientation actually not only for Cern and European particle physics. I think it's the entire field that we are talking about particle physics today. So it says here very clearly as the recommendations is the exploitation of the Large Hadron Collider. It says also about the Higgs. I mean, was the discovery of the Higgs was, of course, in the background of developing the strategy, and the next highest priority collider should be such a so-called Higgs factory with which we will be able to study this particle, this very special particle, in even much more detail than we can do now. And then the future project is the sort of the follow-up of the LHC 100 TeV Hadron Collider. I'll come back to this during this presentation. Now, let me start with the LHC, the Large Hadron Collider. You have seen this picture already, so I can be very quick here. You know, this is a machine where protons and protons are brought in collision at the highest energy ever achieved so far. Also ions, so heavier atomic nuclei. And there are the four experiments, CMS and Atlas, who discovered the Higgs, and then two more, say, specialized experiments looking into other questions. This is how an LHC or a collider looks like. It's, you see all the blue things, which are, I think, the key ingredients of such a accelerator, such a collider. These are the dipole magnets which keep the protons or the ions on the circular trajectory. The experiments, I think we have heard from Juan already a bit more about them. I just want to make one point, that these experiments are huge collaborations. Atlas and CMS are collaborations which count more than 5,000 members from all over the world, about 40 to 50 different countries. And you see here are the maps of Atlas and of CMS, and I used to say that in these collaboration, the sun never sets down, as you know. And then Alice and LHCb, the other two, are a little smaller. Still, they are large collaboration with about 1,500 or 2,000 members here. Now, this is another plot, and I'm built upon the excellent presentation that Juan gave already, is what have we learned about the Higgs over the last 10 years. And one example that I picked, there could be other examples, there are many other examples, is the measurement of these Higgs couplings. As we also learned already, that these Higgs couplings to these other particles that we know there should be proportional to the mass, or in this view, there should be a line up on this trajectory here. And indeed they do. All that we know today is that they nicely follow our theory. But what I find is most impressive is the precision that we have. You see this here is about 10%, or in many cases even lower than 10%. So we could verify the predictions in an impressive manner with an accuracy often better than 10%. Now, what is the future? I pick another example, which is one of the things that we don't know yet, but is extremely interesting, is does the Higgs couple also to itself? Indeed, it should couple to itself. And this has something to do with this famous Mexican head potential, which is actually the basis of this mathematical trick that has been invented more than 50 years ago by Higgs, Englert, Brout, and a few others. And with the existence of the Higgs particle, we actually have just shown that in this formula, which describes this Mexican head potential here, that the first term is correct. Now we are hunting the second one, and in order to get access to this, you see you need to study processes where two Higgses are produced in one collision. And this is not completely out of reach, as you can see. This is a nice example on the right-hand side here is a collision event recorded by Atlas. And you are experts now in recognizing Higgses, and you see here one of the two Higgs decays into so-called B quarks here, and the other one into photons here. But we need many more of them to really establish and precisely measure this interesting thing. And that is one of the primary goals of the future of the LHC, also the high luminosity LHC, to which I will come in a minute. Now, another thing that I want to mention as sort of the prelude to my presentation are the timescale of these projects for the LHC. So if you look back, that the first ideas, the first discussions at Cern on such a machine were around 1980. And the first thing that I personally remember is a workshop on the LHC and the feasibility of the LHC, which took place in 1990. I was a young postdoc back then working for Aachen University. So that was like, for me, is the oldest memory I have on the history. And then you go through and you see here that at some point, end of the 1990s, there was the beginning of the construction, then the first dipole magnets, the last dipole magnet, the first circulating beams, and then it took a few years from the first proton-proton collisions to the discovery. And that's what I'm going to talk about is then about the next big steps, the begin of the high luminosity phase. I'll come to this in a minute. Around 2040, we will, current plans say this, we will operate the LHC for about another 20 years. So you see this spans from the first ideas to the end of the project, more than half a century. Okay, this is here in a bit more detail, the scientific program of the LHC. So, you know, we started, oh, where is my, no, sorry, there it is. We started here around 2009, 10. This was then here the, at 2012, the discovery of the Higgs, you know. We have continued, we are now 10 years later, we are around here. We are just coming out of a phase where we have improved the accelerator and also the detectors. I will tell you something about this. And then we are just about to start then a new period of run, as we call this, where we will operate the accelerator and the detectors that goes around until the end of 25. And then there will be a major upgrade where we will increase the luminosity. Luminosity is the scientific word for the rate of proton-proton collisions, where we will increase significantly. And if you look at the numbers, what we have now, which is essentially here, say 200 of this unit here, we approximately in the next 4 years, we will double this for the experiments, but at the end of our 20 years program, we'll have 20 times more the proton-proton collisions than we have now. So we'll be able to get much better precision than at the end. So this is here what it essentially says. In particular, important here, you see here these red dots illustrate the rate of proton-proton collision, how it will increase in the future. And as I said, by around 2040, or give or take a year, we hope to have 20 times more than we have now. Now, what have we done in the past years to improve this accelerator? Now, it's not only the LHC, because the LHC is at the end of a long chain and complicated chain of accelerators which were used in previous decades, are now still used for some physics, but also as pre-accelerator for the LHC. You see here a sketch of what is sometimes called the Cern accelerator circus, which starts actually here with a new injector, a so-called LINAC, and then you go through the first accelerator, the second circular accelerator, then you go to the third called SPS, before you then end up as a proton in the LHC. So a lot of improvements and upgrades have been done here. One of these is that we'll be able to increase the energy of the protons in the ring. The energy of the protons is essentially limited by the strength of the magnets. So the magnets are good for about 7 TeV. 2 times 7 TeV means 14. We haven't achieved that because at the end, when you really go to the edge of the performance of the magnet, it's getting very tricky. So what we will hope to achieve now in the next years is going from 2 times 6.5, 13 TeV, to 2 times 6.8. And that will again slightly increase the performance of the machine. Upgrades of the detectors, just a few examples. You see here a new detector of the Atlas experiment. As it is lowered, it was towards the end of last year, here into the cavern, about 100 meters underground. This detector, by the way, is called New Small Wheel. It has a diameter of 10 meters. It's only called Small Wheel because there is another wheel which is larger in there. Then you see here another of the big new detectors for the experiments. It's for the LHCb experiment, the so-called scintillating fiber tracker. So in one of these frames, similar size than the other detector, you have about 1,000 kilometers of very thin, 100 micrometer transparent fiber in which serve as detectors. Okay, just to give you a flavor, we are, as I said, about to restart. We had for the first time again protons circulating all around the 27 kilometers end of April, and the detectors were very happy to get so-called splash events, because you don't learn much of physics about that, but you see that your detector is working. It's just when the proton hits the edge of, say, the beam pipe and creates a shower of particles, fills up the whole detector. But this is very useful to actually debug the detectors. And we hope that in a couple of weeks we'll then be able to have the first collisions again, and then we run until 25. So what comes after that is the high luminosity phase. So there the hope is that we will be able to increase the rate per second of proton-proton collisions by a factor of 5 to 7. Why do we want to do that? We want to do that because we can be even much more precise in measuring, for instance, the couplings of the Higgs. These are predictions, and Juan has shown a similar plot that we are then much below the, say, 10% we have now, and sometimes even reaching 2% or less. That is one of the objectives. The other objective is that with more collisions, with more proton-proton collisions you can analyze, you're also more sensitive to the search for new particles. Supersymmetry was mentioned, and this is the example that I brought here. So these are hypothetical supersymmetric particles. One is here with its mass, and the other one on this axis with its mass. That what is this gray area here is the area that the experiments are now able to exclude. So these particles, if they exist, must have masses outside this gray area. With the LHC in 20 years from now will be sensitive to this area, which is indicated here by the broken black line. So a much larger phase space of information of searches is possible. Now, the high Lumi LHC is really a major upgrade of the accelerator. It's about a 1 billion Swiss franc project of investment needed for that. What you see here is, I don't want to go into details, you see here how the underground areas have to be modified, and new caverns and access shafts have to be constructed in order to house then the additional components of the machine, electronics, radio frequency, power supplies for magnets, and so on and so forth. And a lot of this work has been done already. In particular, the underground work we finished, because in the underground, close to the machine, you cannot do heavy civil engineering construction during the time. And this is a photo which I like very much that shows you one of these caverns, which will then, in a few years, be filled up with electronic components and other things. Now, for this high luminosity phase, it's not only a matter of improving the accelerator, it's also a matter of improving the detectors for several reasons, because they have to be able to cope with the 5 to 7 times higher collision rates. One of the things, and Juan also gave us an example, is that the rate of collision is already so high now that when you have a bunch, what we call a bunch of protons colliding with another bunch of protons, there is more than one proton colliding at the same time. It's about 20 to 40 that were the operation conditions. So what the detectors have to be able to find among the 20 or 40 simultaneous proton-proton collisions, the one which is interesting. This is an example. It's a relatively easy one. These are 24 protons you see here in this particular event have been collided, and the detectors are able to find out this is the vertex. These were the 2 protons where the 4 very straight tracks have been created, and these 4 tracks are a candidate for Higgs boson. All the other processes are not so interesting. Now, at the high luminosity LHC, it will look like this. Yeah, so it will become much, much more difficult to do this exercise. So, how do the experiments, the detectors address that, which is the so-called phase 2 upgrade? Here you see a sketch of the Atlas detector, and everything which is written around that will become new detectors which are being designed and constructed now to be ready then to be installed in 26. And you see in particular that what I mentioned in the inner part of the Atlas detector, in this case, new, better detectors have to be installed. In particular, they have to have a higher granularity to separate the many tracks that you have to be able to identify each and every one, and to have a better resolution in space and time. And this is the same plot or the same picture for CMS, and you see a very similar picture here. Okay, so much to the LHC. Let me now come to what we call the Future Circular Collider. This is the next project that we are preparing now and hopefully will be able then to start towards the end of this decade or the beginning of the next decade, as you will show. So this is a picture a colleague of mine took from the top of the Jura in the Geneva area. So here was probably in winter, lots of snow. This is Geneva. You see here the Lake of Geneva. This, by the way, is the Mont Blanc, which you can see when the weather is nice. The orange circles here are the existing Cern collider. This is the LHC, and the smaller circles one, as I said before, are the pre-accelerator for that. The yellow is indicating the plan for the Future Circular Collider, about 100 kilometers in circumference. Now, why do we do that? Again, I go back to the European strategy for particle physics, which, and I remind you, says that an electron-positron Higgs factory should be the highest priority next collider. And likewise, it's also said that there is the ambition to operate then also a proton-proton collider, like the LHC, at the highest achievable energy. So the maximum of the LHC is 14 TeV, and the ambition is to have something like 100 TeV. Here is written. And the strategy asks us to do a so-called feasibility study for such colliders as a global endeavor, and I think that's very important. These kind of projects will not be like the LHC, essentially European ones, but needs to be a global one. And at the next strategy update, which will take place maybe around 26 or 27, we'll have to be able to deliver results of this study. So how would this look like a bit? It's a two-stage project addressing both. In the first stage, the so-called Higgs factory, an electron-positron collider, which, as we'll see, can also work as a so-called electroweak factory, producing a lot of W and Z bosons, top quarks, as well as the highest luminosity. And the second stage should then be a 100 TeV hadron collider, proton-proton collider, with also the option for ions. You see in this sketch here is again the Geneva Lake. This is the LHC as it is now at the border between France and Switzerland, and this is about the area, the 100 kilometer or so circumference for a future circular collider. And then on the right-hand side, you see here some more details on how such an electron-positron collider in this tunnel would look like, and here the same, in the same tunnel, then a proton-proton collider. Okay, this is the organization of the feasibility study. It's the Cern Council, which is our superior governing body, is overlooking this. Now, what can we do with this thing? Now, the model for the first stage, for the electron-positron collider, is essentially 4 different physics goals. As I said, the Higgs factory is among them, and that requires something like a 250 GeV center of mass energy. Why is that? Because the basis of a Higgs factory is this sort of Feynman diagram. You have electron-positrons that collide, produce a Z boson, and the Z radiates off a Higgs, and that you can study. And if you look at this curve here, you see here the cross-section. Cross-section is the scientific word for the probability that it happens in such a collision. And you see here that at around 250 GeV, this is the sweet spot where this process has its maximum probability. And that's why we are aiming for that. And then you can also operate this machine here at the Z, that is 91 GeV. You can go to the WW threshold, 180, and then, which would need some modification though, at the top pair threshold to a 350 GeV. And you see here an operational model. Impressive is the kind of the number of events that you can produce in a certain amount of years of operation. Like 3 times 10 to the 12 Z boson. That's about 1 million times more than we had at LEP a long time ago before the LHC. Okay, how could this be realized? Now, we have to do this feasibility study as told by our council and asked for by the strategy. So what does this feasibility study include? Of course, financial feasibility, that's important, but also technical and administrative feasibility of the tunnel. We have to investigate that there is no showstopper for a 100-kilometer or so tunnel in the area. I will show this in a minute. Also technologies of machine and experiments, and also gathering scientific, political, and other support for this. So this is a sort of a roadmap how this could work. We had a pre-study for a conceptual design already in the past here, then we had the strategy here, we are now here, and we hope that after the feasibility has been proven, we then can, towards the end, as I said, towards the end of this decade or the beginning of the next decade, start with the project. Now, what do you have to study for this? So you see here on the right-hand plot many options how to place such a 100-kilometer tunnel in a very densely populated area like the Geneva area. A tunnel doesn't mean that everything is deep underground. I mean, you need access points, you need many other infrastructure which is on the surface, you need streets and so on this. This is certainly one of the things that we are working very hard now on. And this slide that I got from the study leader there is something which tries to illustrate the size of the problems. Every sentence here, every word that you see here, every circle or so is some problem that might occur, some constraint that you have to place the tunnel. And in all this, we are now working hard to find what is the optimal place where you possibly could put such a tunnel in the Geneva area. You see, it's a highly over-constrained problem. Now, then the next issue, of course, is the accelerator itself, the electron-positron accelerator. This is a plot that shows the 2 things that particle physicists are interested in a collider. Number 1 is the energy, that is here, the higher the better, and the other thing is the luminosity on here on the y-axis. Again, the higher, the better for us. And then you see here a lot of plots. These are electron-positron colliders of the past. And then the 4 stages of the FCC that you see here with different energies and luminosity goals. And you see there is a big improvement needed in all directions from previous accelerators. So there is a lot of also technological effort and improvement and progress to be made to get to this. Of course, all this is based on experiences that have been achieved with the previous generations of accelerators. Now, another thing, of course, is what would such an accelerator cost? The electron-positron version of the FCC. This is our cost estimate here at the moment. So, of course, a big chunk is the civil engineering. It's essentially the tunnel, the access shafts, and all that you need to build there is about 5.5 million Swiss franc. Swiss franc and euro, by the way, at the moment are pretty much the same. Yeah, so it's easy to convert. Technical infrastructure, the accelerators, and also detectors. So at the end, if you add up everything, it comes close to 11 billion. That's our estimate. And this is how you would spend the money. You see that you need about 10, maybe 12 years of construction time from the start, the first stone ceremony, to the moment where you can then really start operation. So as I said, we hope that we will get a green light at the latest, say, beginning of the next decade, and then it's something, an accelerator that might start to operate 45. So that's not too far after the end of the LHC. So that would be a nice overlap. Now, the second stage, which comes yet even after, and I told you that I'm going to give you a perspective for the rest of the century here, it's the hadron machine, highest collision energies. And again, you have here some plot. You see the same parameters again, energy, luminosity. Here are previous machines, the Tevatron. There was a proton-antiproton collider in the US, which has been stopped operation about 11 years ago when the LHC started. So the LHC made a big step, and at least another big step of this is required to build then such an FCC proton machine. Now, the question, of course, is how do you get from 14 TeV of the LHC to the about 100 TeV in an FCC proton collider? So there are two things that determine the energy. That's the circumference of such a tunnel. So you increase it, you go from 27 to about 100 kilometer. That gives you a factor 3.5 in energy. But that's not sufficient. You also have to improve the dipoles. The dipoles that keep the protons on their circular trajectory. And our goal is to go from the 8.3 Tesla magnets that we have now in the LHC and try to double this. And if you double this, then you have the factor 7 that brings you from 14 to 100 TeV. Now, what's the problem with doubling this? The problem is here illustrated on the right-hand side. You see, the issue, namely, is that with 8.3 Tesla, we are about at the edge of the physical limit of today's technology. We are using superconductors, we are using niobium, titanium superconductors, but in this superconductor, you can't increase the field much beyond the 8.3 Tesla. You see here, this is the central field. The year is here, and niobium titanium is this red line here. And with the LHC, we are pretty close to the maximum. So we have to have a new technology, a new superconductor, which can stand higher magnetic field. There is a candidate here, which is called niobium-3 tin, which has a limit which is about a factor, almost a factor of 2 higher than the one of the superconductor we have now. Yeah, and this is actually the goal, to develop magnets based on this, or even so-called high-temperature superconductors, which can go even higher. But as I said, the problem is a little bit here. If you look at the history, if you look at, where is it here? If you look at the history, you see the increase, and these points are all accelerators which use superconducting magnets, dipole magnets. You see, and you extrapolate this, you find out that the advancement in the past was about 2 Tesla per decade only. So, and if you go and see when would you reach here the 16 that you have, you're at around 2050. And this has been realized, and that's the reason why we do put a lot of effort now in this superconducting magnet technology to have high field magnets at the earliest possible moment available. So this is something what it gives a bit more technical detail on this. You have to have not only increase the field, but once you have increased the field, you have to be able to make long magnets. You have seen the LHC magnets about 15 meter long, and that's another path for the R&D. There are a lot of institutes, laboratories around the world working with us, with Cern in Europe and in the US, in Japan, by the way, as well. And I'm in particular happy and thankful that also Spain, Ciemat, is participating in this effort. You see here, I don't want to go into details, some ideas how such FCC magnets could look like inside. And here is, again, a list of parameters of this machine in comparison to the LHC and the high luminosity LHC. You see here the huge step in energy, see the step in the dipole field that we want to make, circumference, and in many other parameters which are there. This is in particular something which also needs a lot of attention. That's the synchrotron radiation power emitted by the proton beams. That's if you turn a particle, then it emits light, synchrotron light. Protons usually don't do that, or very little only, but at these conditions of the FCC, it's going to become a problem, because you can imagine that this radiation would create heat in the superconductors and then break the superconductivity. So this is something, and there are many other challenges that have to be met. There is a global FCC collaboration now. If you look at the numbers here, institutes, companies, countries, and so on, the European Commission is also supporting that. They're spread all over the world. It almost looks like a collaboration like Atlas and CMS at the moment. And this is, a commercial is for interested people. It's the FCC week where this collaboration meets, actually in 2 weeks in Paris. It's a hybrid event. One can also follow this on the internet. Good. If I have two, fine. Then I can maybe also say a little bit about the non-collider program, or diversity program, as we call it. We just heard also previously from that not only the energy frontier, try to get to the highest energy, is important to get more insight into particle physics, in the problems and open questions, mysteries that we have. But there are also other ways to look at this. This is again, this picture I showed already, the accelerator circus at Cern, and you see here at many places, like this one here, like this one here, the AD is particularly interesting. That is a place where we do experiments with antimatter. These people are able to produce anti-hydrogen now from antiprotons and anti-electrons. It's a very tricky thing to bring them together and have anti-hydrogen to look at. And one of the interesting things that they want to do is they want to study the effect of gravity on antimatter. Is it the same as for matter or not? And I hope that in not too far future we'll get an answer to this. In total, at Cern, there are about 20 projects, and I've listed them on the right-hand side, and there are about 1,200 physicists working with us at Cern on these projects. Now, one thing I may spend a minute on this is neutrino experiments. And again, we heard already that neutrinos are very mysterious particles, and there is an experiment in the United States which is called LBNF-DUNE for Long Baseline Neutrino Facility and Deep Underground Neutrino Experiment, which is sort of the flagship program of particle physics in the United States, and is probably also one of the flagship projects for neutrino physics. It's very easy explained. So there is a laboratory similar to Cern, close to Chicago, which is called Fermilab. They have a proton beam, and with this proton beam, they produce neutrinos. And these neutrinos will be sent through the crust of the Earth about 1,300 kilometers or 800 miles to an underground laboratory, a former gold mine, 1.5 kilometer underground here in South Dakota, is it? It's called SURF, for Sanford Underground Research Facility. And at this place here, there will be huge detectors, 2 at the beginning and maybe then 4. You can see the sketches here, which will analyze the neutrinos produced 1,300 kilometers away from that. We at Cern are doing quite a lot for this, for the preparation of the experiment, in particular also to support European groups that want to participate in this experiment. Then in the US, we help them with preparing the detectors and the detector technologies. And one of the interesting thing I find is I want to show you for these huge detectors, they are based on liquefied argon. Argon is a noble gas, and if it's liquefied, it's a very good particle detector. But for neutrinos, because they don't interact with matter, or only very little, you need huge detectors. You see here 66 times about 20 times 20 cubic meter filled with liquid argon. And this is something that we are building at CERN at the moment. We built smaller of these detectors, you see here, and now we build so-called cryostat to liquefy the argon based on this kind of ship technologies here, which are now used everywhere for the transport of liquefied natural gas. And this is also something very interesting, a challenge in technology to apply it from a huge scale and a smaller scale that we know already to this medium time scale here. Okay, that brings me already to the end. Hope I could explain you a little bit of where we think the directions of particle physics will go. in the next years and also in the next decades, hopefully. It's the full scientific exploitation of the LHC, which has a program which is defined for the about next 20 years. We then have, as the next global project, to address the wish for an electron-positron Higgs factory and the ambition to have a super LHC, if you want, 100 TeV proton collider with the FCC feasibility study, which we hope will have results by, say, 25 or 26, which can then be the baseline for future a program, and of course also for decision on the project. And I think this is really a perspective for a scientific program that reaches the end of this century. And at the same time, we do not forget also smaller scale specific experiments which can address, like the neutrinos, very specific questions and mysteries that we have. Thank you very much for your attention.